Howdy. I hope that everybody is well wherever they are. I'd like to go back a little bit, interrupt our discussion of circular motion, and talk a little bit about systems, and in particular system analysis. And as an example of this, I'd like to consider a 5 kilogram block that is on a table with which it has a mu of 0.2, and it is going to be attached by a string to a pulley, and the pulley is going to, the string is going to be in turn be attached to a 10 kilogram mass. And now the question is, what is the acceleration of the 5 kilogram block? Now, you guys have been working hard analyzing this in terms of its component pieces, and you're comfortable with doing a free body diagram. So if we were to analyze this by taking each piece or each part, then we would create for ourselves a quick free body diagram of the 5 kilogram block, and we would show a frictional force here. We would have a weight of 50 newtons down, and a normal force that is pretty clearly 50 newtons that way as well. And for the 10 kilogram block, we have a weight of 100 newtons down, and a tension pulling up. And in our particular example, the pulley is massless and frictionless. And we avoid the newbie mistake. Tension is not 100 newtons because our system is accelerating. Okay, so we're all comfortable with this, and we could even write friction will be equal to mu times the normal. Notice that we're talking about a kinetic frictional situation because our mass is accelerating, and so we get 0.2 times 50 or 10 newtons there. And this immediately gives us a system of two equations for the 5 kilogram block. Tension minus friction is equal to mass times acceleration, and for the 10 kilogram block, weight minus tension is equal to mass times acceleration. And this system does very well with an elimination method, so that we get 90 is equal to 15A, and A is 4 meters, no, A is 6 meters per second squared. Okay, so that's all happy. But I want to come back and consider a second way of analyzing this that actually uses fewer variables and fewer equations. And that is to take a look at the entire system as a single object. And so we call this system analysis. If I take a system analysis point of view, then the 5 and the 10 together can comprise one single object that is going to be experiencing a number of different forces on it. And that one single object, the system, then can be analyzed using Newton's law. So let's consider the one single object and the forces acting on that one single object. I could draw it like this.
Which one is this? Oh,
the whole thing together, that's right. So this whole thing together is going to be a single object. Now to do this, we got to kind of do a weird reference frame. Our reference frame is going to be like this. Here is the positive direction. Yep. And we're going to consider up here any forces here to be in the x direction, and forces here to be in the y direction. So if we take a look, then at just the forces in the direction of motion, then we can say that the sum of forces on our system, which is 15 kilograms, is going to be 10 newtons of friction pulling backwards and 100 newtons of weight pulling forwards. And the weight of this object is irrelevant because it is not pulling in the x direction. And there it is. Notice that the tension in the rope disappears because that tension is an internal force to the system. And so from the point of view of Newton's third law, the internal force of tension here and here cancel each other out. They're equal but opposite forces within the system. And so our sum of forces is simply 100 pulling in the positive direction minus the force of friction pulling in the negative direction, and all that adds up to 15A, which gives me A equals 15A and A is 6 meters per second squared.
So in this case, it doesn't matter if the force is in the x direction or y direction?
Well, we're taking our x direction to be this direction right here.
Like
And
that
so
whole
forces in
thing
the
is
y
x.
direction to be perpendicular to that. We're taking our x direction to be the direction of motion here, and forces in the y direction would be forces that are perpendicular to that direction of motion.
Okay.
Yep.
So this whole thing is
Yes, exactly. Now, if we come back and consider how these equations work out here, notice that we ended up with the same final equation for our system. But here, we got there by analyzing the constituent parts and combining those equations. And when we did, lo and behold, the tensions canceled out so that the math imitated the physics. Sure thing. The math here imitated the physics over here. Does that make sense? So, now let's apply that to a couple of the problems that you looked at last night.
Is that your work?
Might be yours. I think it might be yours.
No, you can use it. It's fine.
Did you guys do 83 last night?
Yes.
Okay.
We did 80.
Okay.
We tried. Pretty good, man.
83 was the after.
Okay. So in 83, we have an applied force. We have M1, M2, and M3. And we're supposed to determine the acceleration and the resultant force on each block. Read me these values. F is equal to
18.
18 newtons.
Mhm.
And then the masses are,
One is 2 kilograms.
3,
Oh.
4.
okay, great. So let's consider now a system analysis of this entire thing. Is there a force of friction?
I said no.
No friction. So mu equals 0. Excellent. So then, if we do a system analysis, then we're going to, then the mass of the whole system is
9.
9 kilograms, and the net force on that system,
Dude, it's like victory.
and the net force on that system is
18 plus.
It's 18 newtons.
period. That's right, 18 newtons period. I do not have to worry about forces internal to the system. And so therefore, that is equal to 9 times A, and the acceleration of the whole system is 2 meters per second squared. Now, I can take that system analysis that I just did, and I can come back and work backwards to the internal forces in each of the constituent parts. How? Because this guy on the very end right here is going to be experiencing only one force, which is the force, the normal force of the 3 pushing him in that direction. So I can say for the 4 block that my free body diagram looks like this. And therefore, the sum of forces is simply Fn, which is going to be equal to mass times acceleration, or 4 times 2, or 8 newtons. So this force is an 8 Newton force.
6.
And, yeah, go ahead, keep on.
6.
Well, let's see here. So for the,
Actually, wouldn't actually be four? Like,
tell me
like
how,
there's a force from two,
there is a force from two.
but since like, Newton's third law, like there is force for four, so there is.
Good, how much?
Same,
So, give me a number.
8.
Thank you. All right, and so now what equation can we immediately create?
I
So-
said.
Yeah, go ahead.
Because I made
Which is, in your head?
6.
6, that's right. So this element is,
2? No, 6, 14.
all right, and then finally for the 2, we're done. Because we already know that the 2 has a 14 Newton force pushing back this way, and an 18 Newton force pushing that way, and so the virtue of analyzing the 2 is to simply check that we did it right. Because lo and behold, 18 minus 14 really is equal to 2 times
What?
2.
Uh,
Yeah. So that for the 2 kilogram, all we're doing is checking.
I think that's an easier way to do it.
Yes, it is, isn't it?
And why is it?
Well, the intent was there. The execution was a little shoddy.
What?
Nothing.
I actually don't know what that word means. What is
Shoddy
it?
means not very well done.
But it also sounds like Sade, which I hear like black people say all the time. I don't know why. It's
Sade.
Okay, well, moving right along.
Thank you.
Late question on the problem before this.
Yeah.
Was acceleration was 6. How do you know which? That's straight down?
It's going to be, yes, it's going to be in the
positive direction.
your direction. Yeah. Yeah, so in other words, this guy will accelerate 60 meters per second squared this way, and that guy will accelerate 60 meters per second squared that way.
So reference frame can be.
Because they're attached to us by a string, every meter that this drops will be a meter that that travels.
Just right, that's 6. Okay.
Oh,
Should
and
it be
then,
back?
in other words, I didn't give it an I or J. Right. So, really, I was just looking for the magnitude of the acceleration with the direction understood.
Okay.
And that's kind of common for these. If there's only one dimension of motion, and here, if we are taking a reference frame to be like, as indicated in green, there's only one dimension of motion, then we're not going to concern ourselves with height and phasor. That still makes sense, yeah.
So reference frame doesn't have to be a straight line.
No, as long as you're being careful about it, yep. And in these cases, it's fairly easy to do that. So let's come back and do a system analysis for number 88. We've got a frictionless plane. They want us to find blah, blah, blah. Okay. And first case, we have, is it M1 on the bottom?
Two
No,
two
two
on the
line is
bottom.
at the bottom.
It's like M and 2M, like
Yeah, like.
No, M and 2,
as measured.
even better. So M,
This is a 2M.
2M's on the bottom.
And then, and
okay,
then,
like so, and then what do we have over here?
capital.
Okay.
And then between 2M and M is T1,
Mhm.
and then T2.
All right, and so our first go at this is with a frictionless plane, and so now let's have a system analysis of this whole thing. First of all, the reference frame, what's our reference frame? Yeah, that's right. And why is it gonna go this way and not that way?
Because it's going that way.
How do you know? How do you know which way it goes?
further into the problem.
Yeah, and it says,
It says, now assume m is double the value, and so if it's static now with just capital M, if you double capital M, it's going to accelerate downward.
okay, fair enough. So in part A, we assume that the whole thing is frictionless, excuse me, in equilibrium.
So which way we do that?
So if in equilibrium, then the acceleration is 0, right? And we can pick any velocity we want, but it doesn't really matter, so let's pick 0. All right. So therefore, in preparation for B, it probably makes sense then that we're going to take this way to be our positive direction. All right? Fair enough. Now do a system analysis for me. Yep. What forces are going to be acting on our system? Be specific.
Gravity on big weather.
When I say be specific, I actually mean QB an expression.
Oh, big NG.
Okay. Notice that the normal force is acting perpendicular to our system.
Right.
Right.
So that's it.
No.
Is the mass gonna? Like, no, not mass, but.
Minus
P2 is a force internal to our system.
Oh. It's 3 mg sin theta.
Yeah. There we go. But now you need to concern yourselves with plus and minus signs.
Minus 3 mg sin theta.
Okay.
5. Because it's been 5.
Well, yes. So if you actually were to split this up into constituent parts, right, then you would have 2 mg pulling straight down, but we are familiar with the whole rotated reference frame thing, and we are familiar with the fact that mg parallel is mg sine theta, and there it is.
Oh, MDM.
Right, and the same thing is going to be true for the other m as well. So notice that the system analysis helps clarify our thinking about what's really going on here. It helps us to take a bigger picture approach.
What about Y?
What about y?
What about Y? And then,
Is our system accelerating in the y direction?
no.
All right then,
Okay.
well, let's leave it alone. When we have to consider friction, we'll come back to
Okay.
that question. But for now, frictionless plane, equilibrium, there it is. And so what we get then is that, what do we get?
So 3M sine theta is
Is equal to n. Exactly. And then we can plug in numbers if you want. Okay. Now, in part B, we have acceleration. Or do we?
That's part
So
C.
that's part C.
Part B is
B
find the tensions in
Find the tensions in both ropes. So now we need to come back and break this into its constituent parts. And what we have discovered is that big M is equal to 3m sine theta. So if we now consider each of the constituent parts,
It says now the mass of big M is double.
not yet.
We're on part B.
Oh, that's for C.
So what does the free body diagram look like for our 2m? Well, we have t here, and we have 2mg sine theta here, again ignoring the y direction. Oh, t1, excuse me. And so I can immediately generate sum of forces on 2m is equal to t1 minus 2mg sine theta, again 0. And on the M, we have, what are the forces on M?
T1, and that one, T2. So, and mg sine theta.
Yes. And we have a value for T1.
Right, so, T2 equal 3 mg sine theta.
Which we could also have gotten by observing the three-body diagram for big M. So notice that the objects on the ends of our system are a little bit easier to analyze.
What if Q1 minus Q1 equals something? Oh, equals 0?
Yeah.
Why? Because, why doesn't it equals to array?
In parts A and B, the system is in equilibrium.
That's why.
That's why.
But if we were to do like the same thing to the beta, would that be equals to no,
Okay, so the word equilibrium means that the acceleration is 0. And if the system is in equilibrium, the acceleration of that system is 0. You cannot have one object in that system accelerating without all of them accelerating because they're attached together by the ropes. Right. So this is for parts A and B. Notice how our system analysis takes place. We consider first of all the system, and then we come and break it into its constituent parts. Now, let's do the same thing in part C. What's happening in part C now?
the acceleration of each object. The volume of big map is double.
Okay. Get it back, please. So how do I mark this guy right here?
Q1,
2 that works. But is that the most efficient way to do this? How should I really write this?
the 6 mg something.
There you go. And that makes a lot more sense
That's
because it
6 m sine
yes.
Ah. There you
That
go.
makes a lot more sense because now it reduces the number of variables that I'm working with, right?
Mhm.
Now let's get a system analysis on this system. Will, you're up.
Some forces, again, let's say some something. I guess some forces in the system.
Yes.
Equals that times acceleration.
Okay, good. Now fill in the details.
Equals 6 mg sine theta. Minus 3 mg.
G and yep. Good. Yeah.
Sounds good.
Yes, they do. And so, yeah. So we get, yeah, right. 3d sine theta. We can do some direct division. And that, as you point out, is equal to g times sine theta over 1 plus 2.
3M plus 6 and 7 plus.
Because that's the total mass of the system. Sum of forces here, total mass of the system here.
But, so in this case, 2M and M become forced out.
In this case, the 2M and M are pulling this way, yes. And that's reflected in this term right here, in the sum of forces. Here, we're just adding up all the masses of our system. Got it. I'd like for you tonight to come back and take a look at a couple of these problems from a system point of view. And see if you can get yourselves to think about that a little bit more.
Can you first base
Yep.
for physics and